Hi, my name is Charles Cowdrey. This is a recording for my CS3003 project. I chose to do the first option, ADT and imperative. I decided to implement C++ features in C. So I have a little itinerary here basically. So if you're gonna do C++ in C, of course you gotta do objects. So you can see that I got my little objects here if they're constructors. So the way I went about this, so I'm just gonna take a look real quick at the constructor. So we have the object struct allocated with a malloc. Um, Go to definition, we have the fields. So typically with an object, you would have member functions. It's an imperative language, so you can't define functions for the struct. But what I did do is that I have all these procedures for it. Most of these are procedures. They just have like a return for an error state. And then I bind them together via function pointers. This is basically just like a vtable. It's how I think virtual functions in C++ work. Is that they are just bound via a secret member variable to a function pointer. Anyways, right. So the member functions are bound, and then you can access them just via the member. When you call them, you have to provide in a pointer to the relevant object, the caller object. This is basically a self variable. In C++ this is hidden. You don't have to manually pass that, but that is how the functions work, is that they are passed a variable to their host object. So that's in a nutshell how I handled the objects. Structure just sets technical values and stuff. So the next thing to get at is generics, like templating. So I did this in a few different ways. Vector generic does it via runtime buffer allocations. So with vector generic, when it's declared, it has its type size, so the size of each object it's going to store. That is passed in as a variable, the fucking object byte size. So when it reserves, it can use that to allocate the right size buffer. And then when it pushes back an object, you pass it a pointer to the relevant object. So we have a void pointer, and then it will find the correct position and its buffer, and then it will copy the memory of the relevant item into the buffer. So that's just real quick, the generic, pretty simple. So this was a little something I cooked up. So I realized that you could use the C preprocessor to create compile time custom typed object declarations. So you can see here that you pass a name and a type. So what we have here is a redefinition of the vector object. It's named a little differently when you do the declaration, but the point is the memory layout is the same. And for the most part, the member functions are the same too. A few of them have their type specified, so the pointer to the data is typed. So this would be an int pointer to a int allocation. When you're pushing back, you can pass in a int pointer instead of a void pointer. And when you when you access the actual objects within it, you can actually get back an int. I have a small wrapper around the reference-based accessor and push function that allows you to pass in the items via value. So you can see that I have the typed one here. You don't have to pass it in via pointer. You don't have to do the void pointer or anything. And here you can actually return by value, which I will just quickly show down in the demo. So you can see here that with the generic vector, you have to push via ref. But with the templated vector, you can push back via value, or you can access via value. You don't have to dereference a pointer. So this templating, this compile time class definition generator is how, as I understand it, C++ works too. You give it the, you have the template declaration, and then when you call like when you are instructing the code to create a templated version of the object, it generates a class definition with specifically that type. So you can see that I have the generator called, and this is like, yeah, this is just a generator. It generates the definition. So there's that. You can see that essentially this typed declaration is essentially it essentially just inherits from generic vector because it has the same memory layout. I'm able to just redefine some of the functions, and specifically in the generic function, I have two functions that I do not typically define. I have the at and pushback. These are the pass by value functions. So these aren't like given a value there in the constructor. They're left as null. Basically as a like virtual or an abstract function that will be declared by child classes, which this does. Right. So I think that covers that. These macro templates also work really well for small value pairs. So like for a templated pair struct, I can use the macro to do it actually where both the values are side by side and you actually have it typed. I'm pretty sure you could do this with a generic using malloc and a little bit of clever code, but honestly, this little macro works way better than that would ever. So the last way I implemented these like kind of generics was this fixed height tree. So this is just a tree with a fixed height of 64 nodes. So the way this works is that you have the 64 nodes, and at the very end of it, it stores a pointer to the object. So when you pass in the object, it will malloc a buffer with the size of the type. So if this was an int, it'd be like 8 bytes, something like that. And then it copies in the data, and it just stores a reference to the like memory buffer. It doesn't like store the value inside the node. So this is pretty convenient. This is kind of the most flexible solution for implementing these kind of abstract types in an imperative language like this that doesn't really support templating. But these also have their own problems, though. Because we're kind of simulating class behavior instead of actually having this all bound together by the compiler, when I go to either add items into or remove items from these generics, because I don't know the type, I don't know the constructor, the copy function, or the destruct or anything like that, I can just delete the buffers. I can free them. But that might leave memory hanging. So I have a vector of strings. Now, each of these strings is basically just a small wrapper around a vector with a couple of helper functions for like string operations. So this vector of strings, if I were to just directly copy them in, just copy the memory of the string struct, that'd cause issues because all these copies would point to the same underlying memory buffer because they all have the same vector object. So what I do is I provide a copy function, which is called while it's like pushing the item into the vector. And so that copies the memory for the vector too. And as it's destructing, if I were to just destruct the raw string memory using free for the entire buffer, it would leave all the vectors for the strings hanging. The memory would just get leaked. So what I have to do is I provide a destructor function for the string, which is called individually for each item in the array before freeing up all the memory. So what was the point of all this? What I wanted to do is that I wanted to implement exceptions. C doesn't really come with them by default. Like it does. You have like assert and abort, but it's kind of sketchy. What I wanted to do was to have exceptions like unknown error, out of range, underflow, overflow, invalid argument. So what I did is that I created a error table which has the error code, which is just an int literal, and associated message for that error. So with those associated, you can call the throw exception function with the given literal, and you can pass in a additional message to display during the error. So what it does is that it takes a error literal and a message. It looks up the associated message for the error in the table, and then it stitches together a final message out of that base error and the provided message in the argument. It will then display that. It'll print it to the console. It will free a couple objects, and then it will either abort or exit, depending on how you have it configured. So to demo these errors, I have a quick demo here. So what I'm just going to do is that I'm going to add some ints to vectors, and then I'm going to read them back. This also just demonstrates feature parity between the generic vector and the templated vector. So if I just run this real quick, you can just see that it reads out the items, it lists them, all that, fairly standard. So that's typical behavior. But let's say I try to read too many ints. So I go ahead and try and read 11 ints from this 10 int long vector. And what happens is that it throws a abort. So I can actually retry here to see the stack frame for it. I can go up. I can see that my index is out of range. Why is that? Because I is 11, but the vector is size 10. So yeah, pretty simple. As a quick demo of the error table to show that this is dynamic, what I'm going to do is I'm going to remove the out of range error. So if I remove the out of range error and I do this again, what I get instead is that I see a unknown error. So we just removed it. Let's add it back, but we're going to rename it. And so you can see here, we got the brand spanking new error. Well, anyways, before I leave off for today, I did realize as I was recording this that I focused a lot on implementing object-oriented features and not really the actual design style of an imperative language. So I did go back and I rewrote some of my string functions to use just direct calls to vector functions. So you can see that instead of calling a member from the object, I'm directly calling the function. And then it's operating on the vector of the string. I already followed this design style for the fixed node tree, but I just haven't really highlighted that code during this video. Anyways though, a fairly small project, not a lot of flashy like demo or anything, but I was really just focused on the actual implementation details. Anyways, I hope you have a good day, and thank you for your time. Bye-bye.